What if I told you your drone could fly smarter even when its GPS is lying to it? There is one algorithm that quietly powers the world of control system and robotics. It is called the Kalman Filter, and in this video we are going to break it down for you. Imagine a drone that is flying in a straight line. The GPS gives us data related to the position of the drone. But the problem is, the data received by the GPS is noisy. The Kalman filter filters the noise and gives an estimate of the data. The Kalman filter works in two repeating steps. First, it makes a prediction of where the drone should be based on the mathematical model of the drone. Then, when it receives the sensor data, it corrects its prediction and then moves on to make the next prediction. This cycle of guessing and correcting eventually makes the guess better and better. Consider this. You and your friends are playing a game of blindfold. You are supposed to catch them, but all you can do is hear them yell. You use your understanding of how fast they are walking, plus their shout, and make a guess about their position. Each time, you make a better guess and finally catch them. This is essentially what the Kalman filter does. Now, before diving into the MATLAB code and simulation, let us have a look at the mathematics that's involved here. We define a state vector x that stores the value of the position and velocity of the drone at a given time t as x of t. The position of the drone at a given time k can be given by the following equation. Here, dt represents a time step. Also, we'll keep the velocity constant, so the velocity at time k will be equal to the velocity at time k minus 1. We can now define a state transition matrix A that can relate the state at time k with the state at time k minus 1 for our mathematical model. The negative sign here represents that this is a prediction or an estimation made using the mathematical model. We also have a state covariance matrix which is denoted by using P of k. Here, Q is the process noise covariance. And just like before, the negative sign tells us that it is an estimate or a prediction made using the mathematical model. The next step is to correct or update our prediction using the data that we actually received from the sensor. We denote the measured position at time k as z of k, which can be represented as a sum of the true position at time k and some noise. R represents the measurement noise covariance. To correct our estimate, we first take the difference between the measured position and the estimated position. The estimated position can be rewritten as the product of two vectors. This vector is familiar to us as the state vector of the drone. This other vector, we can represent it as h. Rewriting this, we get the error in our estimate. The following equations help us correct our position and the process noise covariance and make way for the next predictions to be. Now let us get into the MATLAB code. For our understanding, this code plots three positions. First is the true position of the drone, which will be represented in blue line. The second is the measured position of the drone, which will be represented in the form of red dots. And the third is the estimated position, the one which we got from the Kalman filter. As we can observe, the blue straight line is the true position of the drone. The measured position is scattered all along. This is due to the noise that affects the measurements. And finally, we have the green dotted line, the one which we got from the Kalman filter. As we can see, it is closer to the actual position than the sensor readings that we got. So that was all about the Kalman filter. Stay tuned for the next video. Until we meet again.